So we talked about climate modeling as if it's a monolithic thing, but then we also mentioned parameterizations needed for various things from humidity mixing to ocean mixing to land surfaces and vegetation, land use types, and so on. So obviously this means there will be many models because each country, each lab within a country, each institution, many researchers develop models based on their goals, which may be very specific, which begs the question, how do we know which model is the best? So obviously there is a need to evaluate the models, and under IPCC the projections are done with many different models, which obligates us to do model intercomparisons, which is where the so-called CMIP, climate model intercomparisons, come from. As you know, there have been CMIP 3, CMIP 4, CMIP 5, CMIP 6, and so on. CMIP 4 was never published. We went from CMIP 3 to AR5 in CMIP 5 and AR5, and now we have CMIP 6 and AR6. But there have been earlier also so-called atmospheric model intercomparison projects, where we saw that, and we will see here, that if you have an atmospheric model and it needs boundary conditions, it's easier to just give it some kind of a land surface model and prescribe the ocean with sea surface temperatures, either as daily averages, monthly averages, and so on. Many times they're also fixed to study how ocean is fixed, but the atmosphere is producing variability because of its internal dynamics and so on. So AMIP 6 were done way back in the 1980s to produce many interesting results, and they are very instructive because without coupling to the ocean they can be run much faster. Atmospheric model without coupling to the ocean can be run much faster, just like atmospheric model without ocean model without atmospheric coupling can be run much faster for studies like western boundary intensification, carbon cycle, biogeochemistry, and so on. There are many reasons why you would do that. So let's look at, so models need to be evaluated, and they are done in many ways. We'll just look at very brief examples of how they are typically looked at. So here are the December to February and June to August rainfall. So precipitation climatologies for DJF and JJA, which is a jargon often used, average over 1979 to 2000 from the atmospheric component of the NCAR CCSM3. NCAR is the National Center for Atmospheric Research in Boulder, Colorado. CCSM3 is the Community Climate System Model version 3. They are forced by SST, so here the atmosphere is seeing just the sea surface temperatures. So this is faster, so-called AMIP simulation. Contoured are at 2, 4, 8, 12, 16, 20 millimeter per day. The observed 4 ppm, 4 millimeter per day contour is overlaid in black line. So observed is estimated from satellites and gauges and so on from a product called CMAP, climatology something. Okay, precipitation product. Model data is used to make this, and subsequent figures are courtesy of program blah blah blah. Okay, so you can see that the model has realistic structures in terms of an ITCZ, in the hemispheric symmetries, asymmetries, the monsoon structure here, and so on. And yet, compared to the observations, it has some serious biases. For example, here there is a 4 millimeter contour in observations, but the model is not producing any serious precipitation over there. And there are other biases as well here and here, and so on. Of course, there are details. Does this, because precipitation corresponds to heating in the models and storm tracks here, what is the model doing right. It will be doing trade winds, it will be doing El Niños, it's doing a monsoon, it's doing the so-called Pacific Decadal Oscillation, North Atlantic Oscillation, and so on and so forth. But in the mean state it has some errors, which means each of the modes and their teleconnections, for example, relation between El Nino and the monsoon and so on, will all be slightly imperfect. So it's a question of understanding those imperfections and trying to understand what may be causing them and how to improve them, how to reduce the biases, and so on. So the models keep continuously improving over time. So here again, the 4 millimeter per day contour for the precipitation climatology, again DJF JJA. For CMAP observations, shaded over 4 millimeter per day. Atmospheric component of the NCAR CCS SM3, forced by observed SST. So here it is forced by observed SST as well. Here atmospheric component of the so you are comparing now, what is being compared here? Okay, this is the coupled model simulation, and this is atmospheric component forced by observed CCSM3. So CMAP3 observations, AMIP model where the observed SSTs are forcing the atmospheric component, and the full coupled model. The main point, without going into the details, is that when you force with SST, the atmosphere is seeing real observed SSTs, so it is constrained very heavily. Oh, come on. When you have a coupled model, let's say the atmosphere is a very fast time scale component of the coupled climate system, and let's say it makes a little error in where the ITCZ is or how strong the trade winds are and so on, which affects the ocean. Then the ocean feeds back to the atmosphere. So errors in one component can get amplified by the coupling in the model. Which can be understood better when you do these kind of comparisons of AMIP and coupled models. And also sometimes errors may get cancelled out, so that the right answer may be being produced for the wrong reasons in models. So those kinds of details have to be understood as well. So I'm just going to leave that as an example of how models are to be evaluated and compared. And the other way is to compare different models, not to do a beauty contest, but there are two reasons. One is to understand why one model may be doing better than the other, because there are infinite number of combinations of things that are different between models in terms of convection parameterizations, land surface parameterizations, sea ice models, orography, resolution, and so on, and cloud microphysics, and so on and so forth. Plus the other idea is, we'll see later, ensembling. So if you take multiple models and average them, you tend to smooth out the errors and produce a skill of predictions, simulations, and projections that are better than individual models. There are random errors that tend to get cancelled out, and that is helpful sometimes to do that. Another way to think about it is that let's say slight difference in the initial condition will take the weather in a different direction, and Mother Nature is doing one integration. Given the initial conditions now, Mother Nature is going in some directions and some direction, and we have one weather or climate after one day, one season, 10 years, and so on. Each model may have slightly different errors in the initial conditions, but they all produce different realizations or different places where Mother Nature would have gone given the same initial conditions, or slight differences in the initial conditions. So ensembling the models also gives us the range of simulations Mother Nature could have done but she always gives us one realization because that's what we end up with. So those are the kind of the philosophical approaches, and there are physical reasons why we do that. So here is a model, simulated precipitation climatology 1961 to 1990 from the coupled climate model HAD-CM3 from the UK Met Office for January and July, units in millimeter per day. So without comparing directly to the other models, I can tell you that this model does better than many other models, even though it has coarser resolution than many other models. So it has some things that work very well as a whole to make it better. It's not always easy to say what is the one thing that is different so that we can use this in other models. That's not how it works. There are many things that are different, and it's not always easy to say exactly which combination of them gave it the better simulation that typically happens with HAD-CM3 all the time. So we can also do this with sea surface temperature. So this is the sea surface temperature climatology of the NCAR CCSM3 model, averaged over 1979 to 2000 for December, January, February, and June, July, August. And it has many observed features. Sun is to the south in the boreal winter, so warmest waters are to the south. Sun is to the north, so you see warmest waters are to the north, but it has these systematic biases of colder than observed temperatures typically here, and this feature here extends too far east, which is erroneous compared to observations. Typically here warmer temperatures happen here than here, which is completely reverse of what happens in real world, where there's cold temperatures here and warmer temperatures here, and the thermocline depth in the Indian Ocean tends to be reversed, and so on and so forth. But if you look at the same thing in HAD-CM3, you can see that this is the surface air temperature in degrees Celsius, and again it does much more realistically. This is of course sea surface temperature, and this is air temperature, not direct comparison, but still HAD-CM3 is again better than CCSM3 and many other models. Here is another example. So observed regions of sea ice concentration greater than 15% darkened here for March and September. So March is in lighter shade and September is in darker shade. Obviously end of the northern hemisphere summer, sea ice extent is at its minimum and the winter extent is maximum, so you can see that. And you can see the ECOM5, which is the MPI coupled model, has significant errors here with high concentrations compared to the observed. Maybe it's doing a little bit okay here, but HAD-CM3 again seems to do much better compared to observations than the ECOM5 model. So this again begs the question, does this mean that every component and every region is done better in HAD-CM3 than in ECOM5? And if ECOM5 is doing better than HAD-CM3 in something, let's say like monsoon intraseasonal oscillations, then how do we interpret that? So it gets very complicated in a coupled ocean atmosphere model, ocean atmosphere land model, because errors get cancelled, errors get amplified, and so on. So you have to be very careful in interpreting the model results. This is just showing again the comparisons of different models for El Nino. So this is from observations showing precipitation anomalies, so drier here, wetter here as the warm pool shifts, and you can see that CCSM3 doesn't do it that well, but here MRI GCM3 is doing better compared to observations. This will affect the models, monsoon, El Nino teleconnections, for example, or El Nino impacts on southwest US, southeast US, and so on. So you can see the differences in these regions are seen in the two models as well. So let me leave this here and then come back to further details in the next podcast. In other words, there are many models. Each model does well in many aspects compared to observations. Each models have certain standard biases that are constantly being improved. For example, comparing CMIP 3, CMIP 5, CMIP 6 tells us how things are improving and how things are not improving. And interdifference models also tell us a lot about how parameterizations and representation of processes like sea ice, no sea ice, land ice, no land ice, and resolutions in the horizontal and vertical and so on affect model simulations, and how ensembling of different model simulations give us better simulations and hopefully more reliable projections as well. We will see that in the next podcast. Okay.